Today we want to perform an activity, a simulation activity that will allow us to find the value of Coulomb's constant, which we already know is theoretically 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. We want to find if in fact that's the case. Here's how we're going to do it. Okay, we start off, of course, with a problem, which is always phrased in the form of a question. What is the experimental value of Coulomb's constant? As with every other activity that you do in physics or chemistry or anything else, you have three variables. One is the manipulated variable, and there's only going to be one of those. It'll become clear to you as we go through our discussion here today what the manipulated variable is. Same deal with the responding variable. Which one changes because of the manipulated variable? There's one of them, and that should become clear to you as we go through our discussion today. Control variables, well, there's 1,000 of those. I don't expect you to list 1,000 of them, though. I expect you to list the important one or ones. Sometimes there's 1, 2, sometimes there's 3 really important control variables that you got to keep constant. You have to identify the ones that are really important to keep constant there. Beyond that, hey, list as many as you want. But really what I want to see is the really, really important ones, the critical ones. That should become pretty clear to you as we go on here today as well. All right. So here's what you're going to do. You're going to click on Google Classroom, and there's going to be two things in the assignment for the Google Classroom. One is going to be this template that you see. The other thing is going to be a link to a website that's going to take you to a simulation for Coulomb's law. And that simulation is going to look like what you see at the top of the page here. When you click on that link, the default charges are going to be 1 microcoulomb and 1 microcoulomb. I want you to change one or both of those charges. It doesn't matter. Okay, so that they're different values. Okay, I've got it, you can see as 1 microcoulomb and 5. You can be 2 and 7. You can be 19 and 34 for all I care. Doesn't matter as long as your value for the two charges are different from one another. Just notice this as well, that the units they give you are microcoulombs, which is fine. Okay, those are pretty typical units for charges of objects. Just remember that when you go to do a calculation involving those charges, that you're going to have to convert those to coulombs, right? And to do that, you're just going to tack on a 10 to the minus 6. All right. So once we've got those charges changed, we're going to keep those the same through the entire experiment. We don't want to change those at all through the entire experiment. We want to keep those two charges constant through the entire experiment. It's critical that we keep those the same through the entire experiment. What do we want to change? Well, what you're going to do here is change the distance that separates these two charges. And you're going to do that by clicking on one or both of these charges and dragging them. Drag it to the right to make the distance bigger. Drag it to the left to make the distance smaller. It doesn't matter. I don't care. Just change the distance. Record the value of your separation distance. You can see in my case right now it says 0.0990. And record the corresponding force that acts between them. You can see in my case it's 4.59 newtons. Now we got another force listed here as well. It says 4.59. This second force, the force on object 2, will it always be the same as the force on object 1? It will, right? Okay, if object A applies a force on B, B applies an equal and opposite force on object A. You don't need to record both of them. They're going to be the same. Record this and record this. And then you're going to move the charges again. Get a new separation distance, a new value of R, and then see how F, the force of repulsion, responds to that. Repeat that at least 10 times. Now, because this is a simulation, things work out really nicely, right? You're not going to have any trouble with your apparatus and not properly sensing or playing around with that stuff. So you're going to have lots of time to actually collect the data. If you want to go more than 10 data points, that's great. You need to have at least 10 data points. Your table is going to look like this. Well, a little bit bigger than this because I've only got space for 3 data points. You're going to have 10. But the first thing you record is the value of charge 1. Okay, and it's going to be in microcoulombs. For me, it was 1 and 5. Although, again, for you, it might be 2 and 12. Whatever the case may be, it doesn't matter. Okay, record those two values. They stay the same through the whole thing. Change your separation distance for each trial, and then see how the electric force responds to that for each trial. Now, what do you think you're going to do once you have a table like this? What do we always do when we have a table? Graph it. Graph it. What are we going to graph? Electric force versus separation distance, value of R. That should give you a graph that looks like this. Now, if you were using Excel to graph this, you could draw a nice trend line that would fit that. Google Sheets, I couldn't manage to find a trend line on Google Sheets that would fit that. That's okay. Just don't draw a trend line. Just leave the data points. Just hold on. Just draw the data points. It's not a big deal because you're not actually doing anything with this graph anyways. Okay, you can't. We don't know how to analyze a graph that's not a straight line. So don't worry if you don't have a line of best fit drawn. What are you going to do though? We're going to plot another graph. We want another graph that is a straight line, and it's going to come from this graph. If F versus R gives me this shape, then F versus 1 over R squared is going to give me a straight line. So under analysis, you've got your graph, then you've got a new table, which is inverse of the square of the separation distance, or 1 over R squared, and F. That gives you a straight line. Okay, why does that give you a straight line? Look at my equation. F is equal to KQ1, Q2 over R squared. F versus R doesn't give me a straight line. F versus Q gives me a straight line. F versus 1 over R squared gives me the straight line. If I plotted kinetic energy versus speed, it would look like this. If I wanted to straighten that out, what would I have to do? EK versus EK is equal to 1/2 mv squared, right? So what would I plot in order to make that a straight line? EK versus V squared would give me a straight line, right? All right, so we got to do the analysis of this now in order to figure out what the slope represents and therefore how to find the value of K. You guys know this, you've done this before. Y is equal to mx plus b. That describes a straight line graph. I couldn't do that back here because I didn't have a straight line graph. Now I can because I've created for myself a straight line graph by manipulating the data there. The y-axis is force, m is the slope, the x-axis is 1 over r squared, and b, the y-intercept, will be pretty much 0. Now, what equation has both F and R squared in it? Well, Coulomb's law. F is equal to KQ1, Q2 over R squared. So what I want to do here, now that I have an equation from my graph and I have an equation from my data sheet, I want to cross off F because it appears in both. I want to cross off R squared because it appears in both. And I'm left with the slope is equal to KQ1, Q2. You want to find the value of K. Google Sheets will give you the slope of that graph if you ask it to. You already have the value of Q1 in microcoulombs. You got to convert it to coulombs here now. You also have the value of Q2. Also convert that to coulombs and solve for the value of K. Now this is a simulation, a computer simulation. You should expect the value of K to be pretty close to the real value, right? And what is the real value? 8.99 times 10 to the 9, right? So if you get 2.3 times 10 to the 9, you're probably wrong. You should go back and check your work. If you get 8.7, that's pretty good. Times 10 to the 6, you're wrong. Because it should be 8.99 times 10 to the 9. If you don't get a value that's pretty close, go back and check your work because you've made a mistake somewhere. Finally, after we find the value of Coulomb's constant, which is the value of K, then we got to write a conclusion. And the conclusion is simply, what's the value and justify that. So how do you know? How do you know that that's the value of it? Like essentially describe what I just did in really quick 1 or 2 sentences. You do not need sources of error for this one because this is a simulation. And I mean, yeah, there's going to be sources of error, but they're going to be pretty minimal since um, the data is created data by a computer. So what do you need to hand in? Well, basically the template. Fill in the template, okay, which includes problem already given to you, variables, you got to fill those in. Procedure is already listed in your lab write-up. Data, you got to fill in. Analysis, 2 graphs in another table, and then your conclusion. And it should go relatively quickly for you. Okay, it's not due till Friday, and you do have some time to work on it in class today as we're down in the library.